This is lecture 3C, and we've been discussing thermodynamics. And to start today, I'd like to review some of the thermodynamic functions that we've introduced throughout this particular chapter. First one is enthalpy, abbreviated by H. And you should know the definition of this. It's the total energy plus pressure volume product of a particular system. Now, we normally don't measure the actual enthalpy of any particular chemical, but what we do is we calculate what the enthalpy change is for a chemical reaction. Chemical reaction quite often standing for the system we're studying. So the change in enthalpy, delta H of the system or of the reaction, tells us if the process is exothermic or endothermic if it occurs at constant pressure, and that's because the enthalpy change actually equals the amount of heat given off or absorbed during a chemical process. So if we can measure experimentally the amount of heat released or absorbed in a calorimetry experiment for a chemical reaction, then we can calculate what the enthalpy change of the reaction is. A new function that we introduced this particular chapter is that of entropy, abbreviated by the letter S. It's the energy of a system, the internal energy a system possesses, that cannot be converted into work. And we've actually determined a way to come up with the entropy value for any particular chemical. This is a mathematical analysis of that. It's related to the number of arrangements available to that chemical or that system in a given state. And this is calculated using the Boltzmann equation that we had talked about earlier. So we can actually calculate the absolute entropy of a particular chemical. When a chemical reaction takes place, we can calculate the entropy change of the chemical reaction. So the change in entropy for a system, usually a chemical reaction, indicates to us if that reaction, if that process is becoming more ordered or more disordered. So we now have two different thermodynamic functions telling us different things about chemical reactions. A change in enthalpy tells us whether the reaction is exothermic or endothermic. Change in entropy tells us if the reaction is becoming more ordered or more disordered. Now, when we deal with entropy, the second law of thermodynamics had to do with the change in entropy of the universe, and that tells us something distinctly different than the change in entropy of a system, so I want to point that out here. The change in entropy of the universe, which is actually the entropy change of the system plus the surroundings, actually indicates if a process is spontaneous or non-spontaneous, which is a really important thing for chemists to be able to determine theoretically before they spend a lot of money doing chemical reactions that may not actually be spontaneous. So we can calculate the entropy change of the universe by calculating the entropy change of a particular chemical reaction. That can be done with thermodynamic tables, and then calculate the entropy change of the surroundings. And that's done by calculating the enthalpy change of the system, taking the negative of that, dividing it by the temperature, and then adding those two terms together. That gives us the entropy change of the universe. But that's a roundabout way to calculate if a process is spontaneous or not. There's another way, and that has to do with the third thermodynamic function that we've studied, called the Gibbs free energy, abbreviated by the letter G. This is the maximum amount of energy of a system or a chemical that can be converted into work. And then while we do not measure the actual Gibbs free energy of any chemical, we do measure the change in Gibbs free energy for a chemical reaction. And that tells us the exact same thing that delta S of the universe tells us. So we use this in place of calculating delta S of the universe. The change in the Gibbs free energy, delta G, of a chemical reaction indicates if the process is spontaneous or non-spontaneous. So you need to know the definitions of each of these thermodynamic functions, what their change in values tell you, and then you should know the numerical values as well. For change in enthalpy, exothermic is a negative delta H, endothermic is positive. For a change in entropy of a system, positive means more disorder, negative means more order. Change in entropy of the universe, positive means spontaneous, negative means non-spontaneous. And then for the change in Gibbs free energy, opposite signs now, positive means non-spontaneous, negative means it's a spontaneous process. So we've been calculating changes in each of these thermodynamic functions. The last one we were calculating were changes in free energy, but we were always doing it for standard state reactions, which is really limiting. We're able to figure out whether a reaction is spontaneous or not as long as the reaction's in its standard state. That means you start the reaction with all of the reactants and products present, and they're all in either 1 atmosphere pressure or 1 molar concentration, which is actually not that realistic. We do not start a lot of chemical reactions with all of the reactants and products present, and everything is 1 molar concentration. So we actually want to be able to calculate whether a reaction will be spontaneous if the amounts of the reactants and products are not under standard state conditions. And so we're going to be predicting the change in free energy for non-standard state chemical reactions, learning how to do that today. So what we've been calculating as up to now is the standard free energy change, delta G naught, of a reaction. That predicts spontaneity when the reactants and products are all present in the container in their standard states of 1 molar or 1 atmosphere pressure. If the substances are not in their standard states, then we're calculating just the change in free energy delta G, and that predicts the spontaneity when the reactants and products are not in their standard state. And the way we do that is we will, from thermodynamic tables, calculate delta G naught for a chemical reaction, which tells us whether the reaction is spontaneous or not in its standard state. And then we're going to add to it a little fudge factor that contains the reaction quotient, so that if the molarities of the reactants and products deviate from 1 molar or 1 atmosphere pressure, then the reaction quotient Q can take that into account. And this is going to be the equation you will need to know to calculate the free energy change for a non-standard state reaction. It will equal the free energy change of a standard state reaction, delta G naught, and then we'll add to it RT multiplied by the natural log of the reaction quotient. So let's say we've determined that the standard free energy change at 298 Kelvin is negative 514 kilojoules for the following reaction. 2CO gas plus O2 gas yields 2CO2 gas. How would we determine that? We would go to our thermodynamic tables, handout 5, and we would go standard free energy of products minus standard free energy of reactants, and we would calculate the value for this reaction, and I've just done that for you. Comes out negative 514 kilojoules. So that means we now know whether the reaction is spontaneous or not. The fact that it's negative means it's spontaneous. If the container is starting with 1 atmosphere of CO, 1 atmosphere of O2, and 1 atmosphere of CO2. The value for the standard free energy change is a negative value. That means it's spontaneous. And in fact, the larger the negative number, the more spontaneous it will be. And the lower the negative number, the less spontaneous it will be. So the magnitude of the number has some meaning as well. So let's try this. Let's say we have a reaction vessel. It contains 0.010 atmospheres of CO, 0.020 atmospheres of O2, and 3.0 atmospheres of CO2. Let's see if we can calculate the free energy change for this reaction at 298. So because the pressures of the 3 different substances do not all equal 1 atmosphere, this is a non-standard state reaction. And so we'll calculate delta G by using our delta G naught value, which I gave you at the top, negative 514 kilojoules. And we'll go plus RT multiplied by the natural log of Q. Now they want this at 298, so I'm just going to signify that by writing a superscript on the left side of the delta G and the delta G naught to know that we're using delta G's at this temperature. If the temperature changes, then the delta G value would change. That's not too relevant now in this problem, but it will be a little bit later. And so what we need to calculate is the Q for this reaction. Q is just the ratio of the product pressures to the reactant pressures, each raised to their coefficient as a power, just like the equilibrium constant expression would be. And so if we put in the current pressures of all 3 gases, we can calculate the reaction quotient for this container. So the partial pressure of the carbon monoxide in the denominator, 0.010, the partial pressure of the O2 in the denominator, 0.020, and the partial pressure of the CO2 in the numerator, 3.0. If we calculate our reaction quotient, it comes out 4.5 times 10 to the 6th. So now to use this equation, we're going to use our delta G naught value from above, and we're going to add to it RT multiplied by the natural log of our Q. The R value we'll be using is 8.314 joules per Kelvin. The temperature will be in Kelvin, so when the Kelvins cancel out, our second term's answer is going to be in joules. So that means when I use my delta G naught from above of negative 514 kilojoules, I'm going to have to switch that to negative 514,000 joules. So I'm adding two terms with the same units. So I'm going to use my delta G naught value in terms of joules, negative 514,000. I'm going to add to that R, 8.314 joules per Kelvin times T, 298 Kelvin, multiplied by the natural log of Q. If you multiply that second term out, then add the two terms together, you will get your delta G value in joules, and this comes out negative 476,000 joules, or in kilojoules, that would be negative 476 kilojoules. So once again, that predicts this reaction will be spontaneous under these conditions as it was under standard conditions, but because it's not quite as negative a number, it's not going to be quite as spontaneous as that would have been under standard conditions. Let's try again. Here's the reaction for the ionization of iodous acid in water. And I'm going to want you to calculate a couple of things. Here's the first one. We're going to calculate the standard free energy change for this reaction at 298. So I didn't give it to you here in this particular problem. I'm going to want you to calculate that. You're going to need some data from handout 5, our thermodynamic table. You're going to need the standard free energy changes for each of the reactants and products. And if you want to take a minute and see if you can calculate this on your own, then I will present you the answer in just a moment. So to calculate the delta G naught for this reaction, we're going to start on the product side. 1 mole of hydronium multiplied by its standard free energy of formation of negative 237 kilojoules per mole, plus the next product, 1 mole of the iodite ion multiplied by its standard free energy of formation value of negative 23 kilojoules per mole. We go to the reactant side, we subtract the standard free energy of formation, so minus 1 mole of iodous acid multiplied by negative 55 kilojoules per mole, and then minus 1 mole of water multiplied by negative 237 kilojoules per mole. Moles cancel out in each of the terms. The answer comes out in kilojoules, and so this comes out 32 kilojoules as the delta G naught value. So what have we just determined? We've determined that if you start the solution with 1 molar iodous acid, 1 molar hydronium ions, and 1 molar iodite ions, the forward reaction is not spontaneous. The reverse reaction actually is. So this means that the reverse reaction is spontaneous in a solution that's 1 molar in all 3 of the components given here. Now, that's not that realistic, so maybe let's see if we can answer a question about a realistic solution. Let's say we have a buffer solution. It's 0.500 molar in iodous acid. It's 1.00 times 10 to the minus 7th molar of hydronium ions. That would be the concentration of hydronium ions in neutral water. And then it's 0.250 molar in the iodite ions. So this solution has a weak acid and its weak conjugate base. It's a buffer. So let's calculate the free energy change at 298 for this reaction. So which reaction will be spontaneous under these conditions, the forward or the reverse reaction? So because we're doing a non-standard reaction, we're going to be calculating delta G for this process. And we already know delta G naught. We calculated it in part A. So we've got to work on the second term, RT natural log of Q. Now we're going to be doing this at 298 Kelvin, so I'm just going to signify that. So a lot of times if you don't see a 298 in the left superscript position, it's understood. But anytime the temperature is different than 298, you absolutely should put it there because that's important to know, because delta G changes with temperature and you can't look up delta G naught in a thermodynamic table that's at 298 if your reaction's not at 298. So we're going to try to calculate delta G at 298. The Q for this particular reaction is products over reactants. So that's going to be the concentration of hydronium ions multiplied by the concentration of iodite ions divided by the concentration of iodous acid. If we plug the 3 molarities in that were given in the problem, then the Q works out in this particular case to 5.00 times 10 to the minus 8th. So now we can calculate delta G by using our delta G naught value from before, which was 32 kilojoules. But remember, because our second term is going to be in joules, we're going to have to use this as 32,000 joules. And then we're going to add to that R, 8.314 joules per Kelvin, multiply by the temperature of 298 Kelvin, and multiply by the natural log of our Q value, 5.00 times 10 to the minus 8th. And if you work this out, this comes out negative 10,000 joules or negative 10 kilojoules. So what does this mean? Well, now if you have a buffer solution and you have just pure water and you're adding 0.500 molar iodous acid and 0.250 molar iodide ions, this means that the forward reaction will actually proceed until you reach equilibrium if the solution has these particular molarities. So you can definitely see that concentration variations in reactants and products can change the spontaneity of a chemical reaction. So we now know how to calculate delta G naughts for reactions by just using thermodynamic data from handout 5. And then if you change the standard state reaction to anything that's non-standard state, a little amendment here, just add RT log of Q to that, and you can calculate the delta G for any particular process. We spent our whole last lecture talking about delta G naught, and what's the most important reason for knowing delta G naught? There's actually one other reason that we haven't discussed yet, and it has to do with the concept of equilibrium. If a reaction is at equilibrium, that means the forward reaction or the reverse reaction, neither of them are spontaneous. So that means the delta G value cannot be positive or negative. So if a reaction's at equilibrium, that means delta G is 0. Specifically, that means in this equation, the left side of the equation is 0. Doesn't mean delta G naught is going to be 0. That would only be 0 if equilibrium is established when all the molarities and pressures happen to be 1 atmosphere each, which is actually really rare. It happens at a phase change temperature, but not much else. So when a reaction reaches equilibrium, you usually have strange numbers of molarities of reactants and products, so it would have to be delta G that equals 0 at equilibrium. If that's the case, I can set the left side of the equation equal to 0. And if you're at equilibrium, what is Q? What's the ratio of the products to reactants called at equilibrium? It's called the equilibrium constant. So therefore, if you're at equilibrium, we know delta G is 0, Q is the equilibrium constant. We now have a relationship between delta G naught, which you can calculate theoretically just from thermodynamic data on handout 5, and you can figure out the equilibrium constant of the reaction without ever having to do it experimentally. If I move the second term to the left side, delta G naught equals negative RT natural log of KEQ, or just rearranging it, delta G naught of a chemical reaction that can be calculated from thermodynamic tables is going to equal negative RT multiplied by the natural log of the equilibrium constant. You can memorize this equation. It's one we're going to use a lot, but it certainly can be derived from our generic equation at the top of the slide, delta G equals delta G naught plus RT natural log of Q. So this is why being able to determine delta G naught is a valuable thing to know. By knowing delta G naught, that's valuable because it is related to a reaction's equilibrium constant. We can predict equilibrium constants from thermodynamic data. So let's take this reaction. 4NO gas is in equilibrium with 2N2O gas plus O2 gas. And let's say we've used the thermodynamic tables, and the delta G naught at 298 for the above reaction was calculated to be negative 28.2 kilojoules. So if we're able to do that by going standard free energy of formations of products minus standard free energy of formations of reactants, we calculate the standard free energy change for the above reaction is negative 28.2 kilojoules. Can we calculate the equilibrium constant from that? And absolutely, because this relationship is always true for chemical reactions. If I want to solve for the equilibrium constant, I'm going to isolate the natural log of KEQ on the right side first by dividing both sides of the equation by negative RT. And then I can raise both sides of the equation to E as a base. So the left side of the equation becomes E raised to the negative delta G naught over RT, and then the right side becomes the equilibrium constant. And so this is how we calculate the equilibrium constant from a standard free energy change. Because R is 8.314 joules per Kelvin, then when you use your delta G naught value in this equation, it's going to have to be in joules as well. So this is going to be negative 28,200 joules instead of negative 28.2 kilojoules. So the equilibrium constant for the reaction will be E raised to the negative 28,200 joules divided by the product of 8.314 joules per Kelvin times 298 Kelvin. And if you work that out, you get 8.77 times 10 to the fourth. So we've now determined theoretically what the equilibrium constant for this reaction will be at a temperature of 298. Let's try the reaction for the ionization of hydrofluoric acid. We can actually look up on handout 3 on our class website and get the equilibrium constant for this reaction, which is called a Ka because it's the equilibrium constant for the ionization of an acid. So the Ka for the above reaction is 7.2 times 10 to the minus 4th at 298 Kelvin. Calculate what its standard free energy change would be at 298. And so once again, if we know either the equilibrium constant or the delta G naught, we can find the other. And so I'm just going to solve for delta G naught in this expression here. I know my R value, my temperature is 298, and the equilibrium constant is 7.2 times 10 to the minus 4th. So we're going to multiply R times T, the Kelvin cancel out, giving us joules, and then multiply that by the natural log of 7.2 times 10 to the minus 4th, and I get my delta G naught value at 298 of 18,000 joules, or 18 kilojoules. What does that mean? That means if you have a solution that starts with 1 molar HF, 1 molar hydronium, 1 molar fluoride, then to reach equilibrium, the reverse reaction would be spontaneous, which would kind of make sense. HF's a weak acid. It doesn't ionize very much, so if we're starting with large amounts of the products, they're probably going to reform the reactants again, and then equilibrium will be established with large amounts of HF, but small amounts of hydronium ions and small amounts of fluoride ions. Now that actually brings up an important point about the relationship between delta G naught and the equilibrium constant. It turns out that the magnitude of the equilibrium constant, how big it is, determines the sign of the delta G naught. And we're going to look at a couple of examples to show you how this works, because this is something conceptually you should just be able to recognize. So let's say we have a really big equilibrium constant, 10 to the 5th or something. So it's greater than 1 is essentially what I want to point out. So if your equilibrium constant is greater than 1, let's look at this relationship here. Delta G naught would equal negative RT multiplied by the natural log of a number greater than 1. So what's the natural log of a number greater than 1? You could plug into your calculator 1.3, 1.9, 2, 70, 5,000, 8,000. There's something similar about all those answers. Compare that to putting in the natural log of 0.3. The difference is the natural log of 0.3 is going to be a negative number, but the natural log of 1.3, 10, 100, 1,000, those are all positive numbers. So in terms of logarithms, if you have a value you're taking the log of and it's greater than 1, so if the equilibrium constant's greater than 1, you're going to get a positive logarithm. So the ln term is going to be positive. You multiply it by t and r and the negative sign, that's going to make delta G naught negative. So the moral of the story is anytime the equilibrium constant is greater than 1, the delta G naught value for the reaction is always going to be negative. Or the other way around, if you can calculate the delta G naught of a chemical reaction from the thermodynamic table, it turns out to be negative, you automatically know the equilibrium constant for that reaction is going to be greater than 1. And if you want to think about why that is, except for a mathematical reason here, well, what does delta G naught mean? You're calculating the free energy change when all the chemicals start at 1 atmosphere or 1 molar, okay? And so that means the Q value would be 1, right? This is what's true for all standard state reactions. Products over reactants is 1 over 1. Q just equals 1. So if the delta G naught is negative for a reaction, that means the forward reaction is going to be spontaneous. So what's going to happen? The reactants are going to start turning into products, and then you reach equilibrium, and all of a sudden you're going to have a fraction with a big number of products on the top and a small number of reactants on the bottom. It's going to be an equilibrium constant bigger than 1. So if delta G naught is negative, we know the forward reaction must be spontaneous to get to equilibrium. So more products will be formed, making the numerator bigger, and it makes the KEQ greater than 1. It has to be, okay? Now, if you have an equilibrium constant that's less than 1, let's think about that. If we take the natural log of a number less than 1, and we talked about this a moment ago, if you put in 0.7, 0.3, 0.2, you wouldn't put in -9. You can't take the natural log of a negative number, but any positive value less than 1, it turns out the natural log always comes out to be negative. So delta G naught is going to equal negative RT multiplied by a negative number, and 2 negatives make a positive number. So if you ever have a delta G naught value for a chemical reaction and it's positive, that means when it reaches equilibrium, the equilibrium constant is going to be smaller than 1. And that was the case for our hydrofluoric acid ionization reaction just a moment ago. It had a small equilibrium constant, 10 to the minus fourth. What did its delta G value come out? Came out a positive number. If you have an equilibrium constant exactly equal to 1, what does that mean? Well, what's the log of 1? The log of 1 is 0. Well, that means delta G naught is 0. So if delta G naught comes out to be 0, that means the equilibrium constant has to be 1, which is a pretty rare situation if that were to occur. Okay, so let's see if we can find delta G naught at 298 and the equilibrium constant at 298 for the reaction N2O4 gas is in equilibrium with 2NO2 gas, and I don't tell you anything else. What you would need to do is you need to go to handout 5 to the thermodynamic table and look up the standard free energy of formations of the reactant and product and use them to calculate the delta G naught first. That's what we would have to do. So here's data from handout 5. And if I use my standard free energy of formations for the two substances and go products minus reactants, the first thing I'll calculate is delta G naught at 298. So that's going to be 2 moles of NO2 multiplied by its standard free energy of formation, which is 52 kilojoules per mole, minus on the reactant side 1 mole of N2O4 multiplied by its standard free energy of formation, which is 98 kilojoules per mole. And I get a delta G naught value that equals 6. Means the reaction is spontaneous in the reverse direction, but the question just said what is the delta G naught value, so it's 6 kilojoules. Now, to get the equilibrium constant, we'll use the relationship between delta G naught and the equilibrium constant, and we've solved it earlier for the equilibrium constant. That's going to be e to the negative delta G naught over RT. Just converting the delta G naught value into joules, we're going to wind up going the equilibrium constant equals e raised to the negative 6,000 joules divided by the product of 8.314 joules per Kelvin times 298 Kelvin, and we'll get the equilibrium constant for this reaction. Is it going to come out greater than 1 or is it going to come out less than 1? Because you have a delta G naught value that's positive, that means the equilibrium constant should come out less than 1, and in fact it does. 0.09 would be the equilibrium constant for this particular reaction. Let's find delta G naught and the Ka, both at 298, for the reaction for the ionization of the weak acid, nitrous acid, and water. And I'm going to give you information from handout 5, and we'll give you a chance to try to do this on your own. So if you want to take a couple minutes, see if you can calculate the standard free energy change and then the equilibrium constant for this given reaction. So the first thing you would have to calculate is the standard free energy change, and we would do that by going products minus reactants using the standard free energy of formations of each of the substances in the chemical reaction. So the delta G naught will equal, starting on the product side, 1 mole of hydronium multiplied by its standard free energy of formation, plus 1 mole of nitrite multiplied by its standard free energy of formation, going over to the reactant side, minus 1 mole of nitrous acid multiplied by its standard free energy of formation, and then minus 1 mole of water multiplied by its standard free energy of formation. Moles cancel out in each of the terms, and the answer comes out in kilojoules, and I get 19 kilojoules, which means starting with 1 molar concentrations of all the reactants and products, the reverse reaction is spontaneous, which should make sense for a weak acid. Most weak acid molecules stay bonded together. You will not have large amounts of the product hydroniums and nitrites. If this is the delta G naught value, then the equilibrium constant will equal e raised to the negative delta G naught over RT. And so the delta G naught value is 19,000 joules. So I take the negative of 19,000 joules and divide it by the product of R and T, and I wind up getting an equilibrium constant of this reaction of 4.7 times 10 to the minus fourth, which is the Ka for nitrous acid. So this is what we predict from the thermodynamic tables. If you go to handout 3 and actually look up the acid ionization constant for nitrous acid, it turns out, oh, look at that, 4.0 times 10 to the minus fourth. That's not too bad. So pretty close agreement here. So the thermodynamic data, although maybe not perfect, does predict fairly accurately what the values of the equilibrium constants are. And on our table, that shows us the experimentally determined value of 4.0 times 10 to the minus fourth. Okay? Now, this was all at room temperature, which is well and good. what if we wanted to know the delta G naught and the Ka at 398 Kelvin for this reaction? How would you do that? Well, the problem is the first step. The delta G naught at 398 cannot be calculated by using the free energy of formations given in this table because they change with temperature. So what do you have to do when you're not at 298? If you want to calculate the free energy change, you have to calculate the enthalpy change and the entropy change, and then calculate the free energy change with delta H minus T delta S. So other than 298, we're going to use the fact that delta H and delta S can be calculated at 298, and they will be the same at any other temperature. So the delta H naught at 298 is calculated from the tables, just products minus reactants. So 1 mole of hydronium multiplied by its enthalpy of formation, 286, negative 286 kilojoules per mole, plus 1 mole of nitrite multiplied by its standard enthalpy change of formation. Going to the reactant side, minus 1 mole of nitrous acid multiplied by its standard enthalpy change of formation, and then minus 1 mole of water multiplied by its standard enthalpy change of formation. And the moles all cancel out. I wind up getting kilojoules for this. And so I've now calculated what the enthalpy change is at 298. It's 33 kilojoules. And because enthalpy does not vary with temperature, the change in enthalpy at 298 is exactly the same as the enthalpy change at 398. So now I have my enthalpy change at 398. We'll calculate the entropy change at 298 from the thermodynamic table, products minus reactants. 1 mole of hydronium multiplied by the absolute entropy of hydronium, plus 1 mole of nitrite multiplied by the absolute entropy of nitrite. Over to the reactant side, minus 1 mole of nitrous acid multiplied by its absolute entropy, and minus 1 mole of water multiplied by its absolute entropy. Moles cancel out. The units for entropy changes are always joules per Kelvin. So I get 10 joules per Kelvin. And because entropies do not vary with temperature, the entropy change at 298 is going to exactly equal the entropy change at 398. So we can calculate delta G naught at 398 now by going delta H minus T delta S. So the delta H value, 33 kilojoules, minus our temperature of 398 multiplied by our delta S value, switching that into kilojoules, 0.010. You could have made them both joules if you wanted. That would have been fine. They just have to be the same. But this comes out 29 kilojoules as the delta G naught value at 398, which means this is a non-spontaneous process in the forward direction. If you want to calculate the equilibrium constant for this, we now calculate it from the new delta G naught value. And so we're going to go E raised to the delta G naught at 398 divided by R times 398. I'm just emphasizing the fact that we have to pay careful attention to what the temperature is in this problem. So the value for the delta G naught at 398 is the 29,000 joules. And then we divide it by the product of R times the temperature of 398. And so therefore, this reaction, this ionization of nitrous acid at 398 Kelvin would have an equilibrium constant of 1.6 times 10 to the minus 4th.